So here, it's important that we have that label, 17.2, because with that, we can take whatever guess our neural network outputted, and we can say, okay, that was off by X amount. That was a really bad guess, or hey, that was actually a pretty good guess. And then once we have outputted our guess and we've quantified that, we then want to adjust our weights to somehow make a better guess, to decrease the difference between what we predicted and what the actual correct value was. That's going to be our general strategy. So how do we quantify what a guess is? And I'm going to give you one example of a loss function, but there are different ones out there. So we're going to start with mean squared error. And this is a loss function that you would use to predict a continuous value. So this is something like you're trying to predict a stock price, a home price, some continuous value. And we call it mean squared error. I'm going to start up top. I'm like looking at the piece inside the sum. And I'm basically saying, okay, if y hat, the one on the right, is my guess, and y is the actual label, I just want to subtract them, find the difference, and then square it. So that's where the squared of the name comes from. Ideally, we want to penalize really bad guesses more than, kind of close guesses. If it's really off, that loss will grow quadratically. Also, we want all the values to be positive. That will be important. And then the reason we say mean is because we don't just do one guess. We'll have multiple training examples, as we call it, and we'll want to calculate the average or the mean loss over that batch of examples. So all we're saying here is, okay, what was the difference for the first prediction we had, and the second prediction we had, and the nth prediction we had, and then divide that by n to just get the mean. So after we run through like 16 training examples, we're going to have some number, some positive number, which if it's high, it means, man, we were really off. We had bad guesses for those 16. And if it's low, it's like, okay, we actually are starting to get somewhere, and our model is starting to predict things that are meaningful. Okay, we are going to go through an example of backpropagation. And backpropagation is essentially going to help us learn one really important thing, which is how do we know how to change our model weights in a way that decreases the loss, right? That is our goal. The loss is the difference between our predicted values and the actual values, and we want to decrease it until we predict the correct values. So in this example, I have one final output node, and I have two nodes before that, A and C. And there could be many other layers before that. We're just looking at the very end of our neural network here, because we're just going to start with this, and it'll be simpler that way, and you'll see how it extends to the entire neural network. In this example, our n is 3, meaning we have 3 training examples that we're calculating the loss for, and we want to do backpropagation for that. So in this, just my notation, I have y1 hat, y2 hat, y3 hat. That's our predicted values. y1, y2, y3, that's the actual correct values. And so if we expand the sum from the loss we saw earlier, this loss with summing over n and dividing by n, we're going to have 3 examples. I see I left n as a variable. I didn't say 3, but you can just imagine n equals 3. And we're going to compute the squared difference between each one. Okay, so how are we actually going to do this? We are going to do calculus. Hooray, math 6A, if you guys have taken it. If not, we're going to walk through it. But essentially, we want to find the derivative of the loss with respect to a weight. Remember what a derivative is? A derivative is a rate of change. So if I have the derivative of the loss with respect to a weight, and let's say it's some number like 5, I'm saying, okay, essentially, if I change at this little point, if I change the weight at a rate of 1, it's going to increase the loss at a rate of 5. And that's very helpful information for us because that tells us how the weights actually affect the loss function. Okay, let's get into it. So in this first one, I want to look at the first example, y1 and y1 hat. And in this case, the inputs from A and C were A1 and C1. The first thing I'm going to do is I'm going to take the partial derivative of the loss with respect to y1 hat. y1 hat is my predicted value. Here, I'm doing the power rule, The squared comes down as a 2. Y1 hat is negative, so we have to do the chain rule, bring the negative out, and it's still divided by n. Calculus, this should be, if you guys have taken 3A or 3B, this should kind of look somewhat familiar to you guys. And if the partial derivative is essentially saying L might change due to other things, but right now we're just looking at how it changes due to y1 hat. Okay, what is y1 hat? And y1 hat is a linear function, as we said before. It's just the weight 1 times A1, which is the output of the previous node, plus weight 2 times C1, which is the output of the C node, plus some bias. Well, that seems like a pretty easy function to take the derivative of. And if we do, and we take the derivative of y1 hat with respect to weight 1, it's just A1. That's all it is. Right? So now we know two things. We know how the loss changes with respect to our guess, and we know how our guess changes with respect to our weight. What do we do now? We use the chain rule. Here, underlined in red, is what we cared about. That is the loss, the change of loss with respect to weight 1. And we did it by multiplying the partial derivative of the loss with respect to y1 hat by the partial derivative of y1 hat with respect to the first weight. You can see the denominator cancels with the numerator in the next one, and we're left with the term on the left. And I multiplied A1 by that term up there. And this is left as, this last thing to the right is left as variables, but in actuality, it's going to be some number, right? Like, we know what A1 is. When we did this, okay, I'm going to use some terminology. When we did this forward pass, a forward pass meaning we took our input data and we fed it through the neural network to get an output. A1 was an actual number, right? So that's a number that we know what it is. Y1 is the actual correct value. We know what that is. Y1 hat is our predicted value. We know what that is. So this is some number. And we're going to keep track of this number. If it's -5, it means that increasing the weight by 1 might, decrease the loss by -5 in this specific example, but only in this example, right? We've only done it for one example. In fact, we would need to also do it for the second example. So here I've highlighted in red y2 hat and y2, and I've also in red said A2 and C2. The reason I highlight that in red is that as we go through each different training example, the outputs from previous nodes are going to change, right? This is like saying, okay, first we had an image of a dog, and that produced some output, but for the second one we have an image of a cat. And so A2 and C2 are going to be different values, and Y2 are the correct label is going to be a different value as well. It's going to be some number that represents a cat instead of a dog. Although in this case, since we're doing mean square error, I should preface, we're probably not doing classification. We're trying to predict a continuous value. So maybe a better analogy would be that before our stock price was NVIDIA and we wanted to predict that it was going to the moon. And in this case, we're looking at IBM and that's going down. Point being, A2 and C2 have changed. So we need to recalculate this derivative with respect to the same weight. So this looks the same. This partial derivative still looks the same. The only difference is that now we have a different correct value, and our model outputted something different this time. But it's the same process. Now, our weight is still the same, but when we take the partial derivative of the second of what our model outputted, y2 hat, with respect to the weight, it's A2 now. But it's the same process. We are going to do the chain rule. and we're going to multiply these two values together, this will be a different number. But it will still be a number that we can calculate because we know a2, we know y2, we know y2 hat, and we know n. So I did this for the first example. I did this for the second example. I'm not going to go through it, but in this case, we would also do it for the third example. And the reason we do it for all of them is because we want the total derivative, not just partial derivatives. So here, we want to know across all our training examples, how does the loss change with respect to this weight? And let's say that in the first example, increasing the weight would have increased the loss. But in the second example, increasing that weight by some amount would have actually decreased the loss a whole lot more. That's important. So we want to sum up each contribution of these partial derivatives across all the training examples in this batch. I've labeled it n here, but before it would have been 3, right? We would have calculated the loss, the partial derivative with respect to weight 1, by doing this chain rule for the first example, the second example, and the third example, and we would have summed it all up. And that would have been the total derivative of the loss with respect to that specific weight. So we've done all of that, but that is just one weight in our function, in our neural network. We have more. So what about if we extend this another layer back? So here we have our output, but we have 3 nodes, B, C, and D, and we have A before that. The idea of needing to sum each contribution matters even more now. Why? Because A does not only affect Y through B, it also affects it through C and through D. Meaning, if I increase a weight in A by 1, it'll increase its output, maybe, let's say. And if it increases that output, that's going to affect D because D has an input which has now changed. But it's also going to affect C because C also takes as input A. And so does B. All 3 of them take as input the output of our neuron A. So here, we have to calculate more partial derivatives because we need to calculate the partial derivative of the loss with respect to that weight in A, once through how it changes the loss through B, once through how it changes the loss through C, and once through how it changes the loss through D, and then sum all of those up. And then we need to do that through all training examples in our batch. So here you can imagine I'll use this word gradient, which is essentially just this derivative that we're calculating. It's accumulating. We're as we go through each training example, as we go through each path that it contributes to the loss, that number is accumulating more and more. Okay. Now is when we actually want to use this information to do something valuable. If you've taken 6A, you've probably heard of what the gradient is. And the gradient here, which we use the Greek letter delta to signify, is essentially a vector of the change of the derivative of the output with respect to all of our inputs. In the context of neural networks, what does that mean? That means that our outputs is the loss as we are trying to decrease. And we have all of the weights of our neural network, right? At the end of this, we took we found the derivative of the loss with respect to weight 1. We want to find it with respect to weight 2 and weight 3 in all of our weights. And we have this vector of all the derivatives. And if you remember, if you took Math 6A, and if you didn't, that's okay because I'll say it now, this vector gives us the direction of steepest ascent. What does that mean? You can think of the loss function. The loss is a function of all the weights. It probably looks like some very high-dimensional curve. And I guess I'll just draw in 2D. Oh, that's a terrible one. We can imagine in 2B, it's some crazy, curve, but in super high dimensions, it's even crazier than that. You can think of, in your head, trying to think of some direction. And that direction tells you if you move a little bit to the left, to the right, up or down by adjusting any of the weights, how much does it change the loss function? The reason that it matters is because we want to decrease the value that the loss outputs as much as possible. Does anyone have an idea of how we can decrease the loss? If we know what the gradient is, which gives us the direction of steepest ascent. Yes?
Subtract the loss function by the negative gradient.
Right. If we know the direction of steepest ascent, and it probably is a little bit of a hint by the name, we want to descend. So we travel in the direction opposite to the gradient. We take the negative of the gradient. Okay, so this is what our update looks like. W prime is our new weights, and we want to take all of our current weights and subtract them by the gradient, which will essentially move us in the negative direction. The thing is, this can be a very noisy update. What do I mean by that? I mean that let's say you have some, 3 examples, and it happened to be that, those stocks were outliers if you're trying to predict stock values. And so, your model learns, okay, clearly, these stocks are going amazing. I should learn that to output higher values in general. That might not be true across your entire data set. That might only be true in this small case. So we include this alpha, which is essentially a learning rate. And what we're saying is that each time we make an update, we only want to make a very small update. Meaning we don't want to, look at the direction that's steepest and just dive off of the function and hope that we end up somewhere, super low, because it may be that actually we're diving straight into somewhere that goes up, right? That's very noisy. So we want to take this alpha, which will be something like, a small value like 0.01. For example, though, that is what we'll call a hyperparameter, meaning it's something that you can tune manually. So if it's 0.01, then whatever the direction is, it's going to be a very tiny vector in that direction, and we're going to take a tiny little step to change the weights and hopefully decrease the loss a little bit. So here I have a little curve, which is the loss with just respect to one weight because it's easier to visualize. And although, it's going to be much higher dimensional. But in this case, I have 2 arrows which kind of represent maybe the direction, right? Because the direction of steepest descent, if you're at the red point, is down to the left because the steepest descent is up to the right. Seems pretty straightforward. If you're in green, the direction of steepest descent is down to the right. Question for you guys. If you end up in red, how do you know that you shouldn't go to the left? Right? Because it appears to them that they should adjust the weight downwards so that they can decrease the loss. But they don't know that if you moved all the way to the right, if you went up, increased your loss a little bit, and then decreased it, you would actually reach a lower loss, right? That's a local minimum to the left, but that's a global minimum to the right. So how could we perhaps deal with this issue? Like, how could we know when we're on the red one to move over to the green one? Does anyone have any ideas? Yep.
Simulate it immediately. So just randomly jump around if it goes up. See if it gets at that distance.
Right. So essentially, all we can do is add some noise, add some randomness to it. Because the truth is, we can't know, right? We can't know if we're over to the left that we should actually go to the right. Because all we have as information is the gradient. All we know is that we should move to the left to decrease the loss. So our only hope is that by adding some randomness to how we initialize our weights, or maybe to how we perform our updates, that we'll explore more, we'll get lucky, and we'll be able to find the global minimum. Yes?
Well, like how often do you randomize these weights? Like, is it kind of like every time you take that step, you're like, oh, we're gonna tweak this weight, like we're gonna randomly select a weight and we're gonna change it in an unexpected way?
Not exactly. So like you'll randomly initialize your weights at the very beginning, or use some specific thing like a Xavier distribution is what people will use sometimes. But more the idea being like, okay, when it's a reason why, for example, like we could take our n when we did the previous, when we had n examples that we calculated, the loss for, we did backpropagation for. If our n is very large across our entire training example, it's probably a little bit less noisy or a little bit less random because we've seen a ton of training examples. So sometimes we actually want it to be a little bit more random, and so what we'll do is we'll decrease the n to be something small, because there we're saying this is actually not entirely, this is not maybe as accurate as it could be, but that little randomness of using a smaller n could help us, be more stochastic. Good question. Yes, follow up?
How many minimums can you expect there to be? Like how many, when you're training a network, is there some rule for how many minimums you can expect there to be? So like, okay, in that example, there were 2 minimums in the whole,
Right.
in the whole loss. So you could say, okay, well, I found 5 out of the 10 minimums.
Well, the truth is we don't know, and the reason being is that you have to remember that this is super high dimensional. Like how would you go about, knowing how many minimums there are? You have like thousands, millions of dimensions. I mean, millions is, but yeah, like you have so many dimensions. Like how could you even figure out how many minimums it is? It's an impossible task, which is kind of why it can be finicky. Training neural networks can be finicky.
Do you ever find the global minimum ever?
I mean, probably not. No. Yes.
Yeah, just to kind of add on to Casey's question. Well, from what I understand is like in like a real training scenario, it will be like more or less like a 3D graph where it will be in the shape of like a Lagrange saddle, and then like it will flow downwards, and then the goal will be kind of to find a minimum intercept within like little like the I guess like downward curves that it will have. But it seemed like a 3D format. I'm kind of wondering, like, would you do the same randomization where you jump by inputting like just random amounts of noise? Would you still do that? And like, you see like a Lagrange saddle?
Well, like, I do want to say too, like there are different methods. Like when I mention like add some noise, like okay, so stochastic gradient descent says let's use an n of like 1, and that's very, very noisy. But like a lot of people will use an n of 16 or 32. Like it's very, like it's customizable, and even then that's just one version of gradient descent. There are other ones, like there are lots of different variations on it. In terms of your particular example of a saddle point for, I don't know like what the best method would be. I'm not sure. But I can talk to you afterwards. We can talk more about it. Okay, that is gradient descent. So this is the recap using some words that maybe might sound a little more familiar. So we initialize weights as random numbers. Maybe we are a little smart about it. We're not going to get into it, but there's different techniques of how you might want to initialize your weights. And then you want to, iterate. We're essentially, this is optimization. We want to iterate and slightly change weights, right? So we do some n amount of forward passes, which is the size of our mini batch, right? Could be 1, could be 16, could be 32. We compute the average loss, which I gave you guys an example of the mean squared error, where you take the difference, you square it, you find the mean of that, but there are different loss functions. So that's another choice that you, as a engineer are going to have to make. If you're doing something like classification, you might use cross-entropy loss. That's more trying to predict a probability distribution rather than a continuous value. So that's an engineering decision that you have to make. So we're going to perform backpropagation, which all it really is calculating derivatives. And even in the nonlinear activation functions, where that derivative might be complicated, it's still like we know what the derivative is. So underneath the hood, like it's not too hard to say, okay, the derivative of the hyperbolic tangent nonlinear activation function is just, I don't know it off the top of my head, but it's something, e has exponentials in there, and you can just like compute it. You can calculate it. You know it. So you'll do that for every weight, and you'll do it for all your n examples, and you'll accumulate the gradients until you have your vector, your gradient vector. And then with that information, we'll take a small step in the direction that decreases the loss via alpha. And we're just going to want to iterate through that. And that is essentially how we do deep learning, in quotation marks. We're adjusting these weights. Okay, that's kind of the gist. Any questions? Yes?
How do you decide the number of thinning layers to use?
That's a good question. So there's amount of layers and amount of neurons per layer. I mean, it depends. I would say that the question is, like, how complicated is your data? Like, how big of a network do you need? Because the more neurons you add, the more computational complexity. So ideally, you want to get away with not that much, but it's a balance because maybe if you have just a few, you're not actually able to like understand the pattern that you're trying to actually like see and predict. Like maybe the neural network, if it just has 2 nodes, like how is it ever going to understand language? This is where you see like some things are very high dimensional in nature, and so you need a lot of neurons to be able to actually meaningfully capture that information. Yes?
Yeah, so you said you wanted to perform backpropagation to calculate the gradients to sort of like update the loss rate. But maybe like, I noticed in the 2 activation functions that you showed, the gradients can be really, really small if you have like really, really big values as the input. Like, doesn't that mean that your neural network will sort of like stop learning and get killed? Because there's like a very tiny, tiny gradient update, or maybe 0 gradient update.
Right. Are you perhaps referring to vanishing gradients? Yes, that's a good point. And actually, I'm not entirely sure how to deal with that. Do you know? And can you say?
I mean, this is the problem for sure. Like, I know with the, like, you can't just blindly use activation functions like ReLU. If you want to pull up the slide.
Yeah.
Like, even though I know I've heard it's really popular, right? Like the ReLU activation function. But sometimes you might incorrectly say like, oh, my neural network is not actually learning anything. Like
Right.
its accuracy is really low, and maybe that's the reason why. Maybe you'll have to like experiment.
Right. That's a good point. Thank you. Because I blinked a little bit. But that's an issue with ReLU also because for all negative values, we have y equals y equals 0. Like, because we have that rectified linear unit, what is the derivative? The derivative is 0 there. If you're all the way over at -3, like, how are you ever going to take a gradient and move, further over to the right? So that is an issue with that, with that activation function. Whereas, for a hyperbolic tangent, the derivative is non-zero throughout. But even still, if you had a super large value, your derivative is small, because it is asymptotic. So, okay. A few questions I came up with on my own. So we talked a little bit about, what size mini batch you might want to have If you have just one and you do pure stochastic gradient descent, then it's quite noisy. If you have more, then it's less. The learning rate alpha was what I mentioned, which is like kind of how big are your steps. That's a trainable hyperparameter. Hyperparameter meaning like when you're performing gradient descent, you're not actually updating it, but like you as the engineer are figuring out how you want to change it. And also how long to iterate for. This can come down to overfitting. So if you train your neural network for a long time, you'll notice that it starts to sort of memorize your training data. In other words, in the representation of the neural network, it's able to say, okay, this specific example, I know it has this specific output. And that's not good because the whole point of our model is we want it to generalize, right? We want it to say, if you have seen data you've never seen before, can you actually figure out what the correct output is? So that leads us to how to measure performance. The point is, like I said, we want it to be able to perform well on data it's never seen before. So typically what we'll do is we'll split between training data and testing data. You might see stuff like an 80-20 split. 80% of your data is for training, 20% is for testing. That way you can kind of evaluate your performance and say, hey, I trained it, but then it saw these new inputs I'd never seen before, and it calculated close to the correct output. So then you might ask yourself, okay, why do weights end up in the way they do? Like, why did this weight end up as 1.2 instead of 2.5? Or even like you were asking, Casey, like, how many minimums are in the loss function? Like, what does that mean exactly? And one thing that has been a large area of research is interpretability, because neural networks seem like from the outside a lot like a black box. Meaning like, okay, I can't really explain to you why this weight ended up as 3.2. For some reason, in our calculation of the gradients, led to some minimum in the loss. But like, why is that the case? We don't really know. It's a black box. And that's why there's been a lot of questions like, okay, like, do we actually know what's going on? Can we control it? Like, when you see bias, a lot of people will say, okay, there's bias in neural networks. It's hard to notice except for just looking at the output, because you don't know, that the neural network has some notion of like race. Like, you don't, like, how do you inspect the weights and say, I see that this weight, has some race bias. It's very hard to actually interpret. Okay, last thing. This is kind of the most vanilla architecture, which is called feed-forward neural networks. But there are other flavors out there. I've just listed a few. Convolutional neural networks, usually for spatial data, like images, where like geometrically it's important what this pixel is related to the pixel below it, and to the right, and to the left, and the ones nearby. Recurrent neural networks for more like sequence data. Transformers are a pretty popular architecture, which is more for natural language processing, though it's used in general also for sequential data. So this is where there's a lot of, beyond just the most vanilla basic, there's a lot of tweaking, a lot of engineering that can happen. But yeah, that is your introduction to deep learning. Thank you guys for coming. Yeah.